Making a point. Well, I'm making a point. We've been doing all the same math over and over again. So tomorrow there's going to be a quiz on whether you can do this math. The chart will be there on the quiz. It won't be there on the test unless you're willing to take a penalty for it. Okay? Does that make sense? So, all right. Okay, so I want to make a point about this stuff. So here's a problem just like the one on the second bell word question today. The way I could say it's the same as this, like the second bell word question today, is they're both in liters. So I'll use the same methane reaction every time today, so we don't have to rewrite that every time. So how many liters of CH4 are required to completely react with 17.5 liters of O2? So we start off with the 17.5 liters of O2. And then we follow that same chain. What unit do I want to get rid of? Well, the one they gave me. Liters of O2. That's got to go on the bottom, and liters of O2 I can turn into moles of O2. They didn't give me moles, so I'm going to turn it into moles. So 22.4 liters of O2 is 1 mole of O2. Because we're at STP. Works for every gas. And my liters of O2 have canceled out. Now I need to get rid of moles of O2. So moles of O2 is going to go on the bottom. And the reason why I change into moles is so I can change chemicals. So I'm going to go from moles of O2 to moles of CH4. And there I get the numbers from the equation. There's a 1 in front of CH4. There's a 2 in front of O2. Now, I got to get rid of the one on top, moles of CH4. It's got to go on the bottom, and moles of CH4 I want to, moles of CH4 I want to turn into what they asked me about CH4, which is liters. What volume? So I'm going to go from moles to liters, and liters is always 22.4 liters in 1 mole. And you push those buttons, 17.5 divided by 22.4 divided by 2 times 22.4, and you get 8.75. Yeah.
Can we not just cancel out the 22.4 liters?
Yep.
We have basically just 70.5 divided
By 2. Yeah, so basically, yes, what you're saying is that what we basically did was we could cancel out the 22.4 liters here and the 22.4 liters there. So all I really did was take 17.5 and divide it by 2. Wouldn't it be nice to do that without, because every time I start with liters and end with liters, it's going to do this. The liters will be on the bottom here, and the liters will be on top here, and they'll cancel out. So every time we do it in liters, we're going to run into the same situation where they cancel out. Wouldn't it be nice to skip writing all that stuff? Wouldn't it be nice to say that we can go from liters to liters? That I could say, but which means I'd have to interpret this equation in liters. Can I do that? The answer is yes. Okay. Because Avogadro told us that equal volumes of gas at the same temperature and pressure contain the same number of particles. Equal volumes of gas at the same temperature and pressure have equal numbers of particles. That's where we got the 22.4 liters equals 1 mole. Because 22.4 liters always has the same number of particles, 1 mole of particles. Okay. Now, Avogadro, this is called Avogadro's hypothesis. It's not called a theory or a law because he was right about it, but he was right for the wrong reasons. He said they all take up the same amount of space because they're all the same size. That wasn't true. So it didn't get made into a law or theory because what he said wasn't right. But the fact that it works does work. It just works for a reason he didn't know. Because they just discovered that there were particles. Fact is, the reason why they named it the number after him, because this gave him a good way of figuring out the number. So, and he was one that said that number is an important piece. Equal numbers of pieces. And moles are just a number of pieces. That's all a mole is. A mole is just a big number of pieces. A dozen's a bigger number than the regular number. A mole is a much bigger number. So, we said we could read our equations in moles. But since equal moles have equal volume, as long as they're gases, I can read them in liters. You can treat the reactions as if they happen in liters, as long as you keep the temperature and the pressure the same. So this brings me back to, remember I decomposed water in those 2 glass tubes? We can see that it was made up of hydrogen and oxygen. But remember, the hydrogen was always twice as big as the oxygen. Because in the balanced equation, it makes 1 mole of oxygen for every 2 moles of hydrogen. So we can go straight from liters to liters. And what we'd use is the numbers out of the equation. So they happen liters at a time. Okay. So as long as you keep the temperature and pressure the same, you can treat them as liters. So that means our diagram, right? The problem we just did, we went from liters here, turned it to moles, turned moles into moles, and then turned that into liters, right? We could have gone straight from here to here, just using the number from the equation, using the coefficients from the equation. Okay? We would have got the same answer. So it's okay to go from liters to liters. So how many liters of CO2 at STP are produced by completely burning 17.4 liters of CH4? 17.5 liters of CH4, sorry. Okay, so same equation. Start off the same way, right? 17.5 liters of CH4. Set up my conversion factor. And I could do this like we did the last one, liters to moles, moles to moles, moles to liters, but now we just said I can go from liters of CH4 to liters of CO2, and they're both ones because CH4 has a 1 and CO2 has a 1. Make sense? If it had been H2O, it would have been 2 liters of H2O. Right? So just use the coefficients. 17.5. Because it would have been really annoying for you to write, take it divided by 22.4 times 1 divided by 1 times 22.4, and everything would have canceled out, and you would have right back where you started. So it's just a shortcut for what we're doing. Either way gets you the same answer. This way is just a little faster. And the other one shows up here. How many molecules of H2O at STP are produced by completely burning 5.8 times 10 to the 22nd molecules of CH4? Oh, what the heck? Why'd you move in? Don't do that. So I start by where I start them all, 5.8 times 10 to the 22nd molecules CO2. I want to get rid of molecules of CO2. Oh, is it CH4? That's CH4, sorry. I don't know why. Luckily, I haven't done anything that's going to affect that yet. CH4. And molecules I can turn into moles, right? Molecules become moles. CH4, because 1 mole is Avogadro's number. Not enough room on there. 6.02 times 10 to the 23rd molecules of CH4. Then I want to get rid of moles of CH4. And the purpose of changing to moles is so you can change chemicals. So I'm going to have moles of a different chemical, and the chemical I wanted was H2O. And there's a 2 in front of H2O and a 1 in front of CH4. Now I want to get rid of moles of H2O. And turn it into what they asked me for, which is molecules of H2O. And 1 mole is 6.02 times 10 to the 23rd molecules. Yeah, you noticed a bunch of things cancel out again, right? So I'm not going to type the 6.02 times 10 to the 23rd, right? It's on the bottom, it's on the top. It cancels out. It's right there, it cancels out. So all I have to do is take 5.8 times 10 to the 22nd and multiply it by 2. And I get 1.2 times 10 to, I got 1.16. 1.2 times 10 to the 23rd molecules. Got 1.16, and with just 2 numbers, it's 1.2. They cancel out again. So do we need to write them?
No.
Hey, and actually, we already know that we don't need to write them, because the first thing we did was read the equation in particles. Isn't that the first? We got a balanced equation in this chapter. The first thing we did was say we can read these things in particles. So my equation said 1 molecule of CH4 will make 2 molecules of H2O. It actually said that when we translate it to molecules. That's why you want to translate it to particles, is because then you can just do this. That 1 molecule of this will make 2 molecules of that. Because In molecules, it works. So we can do that same kind of shortcut with pieces that we could do with liters. And it's not because the math works out, it's because we can read the equations in molecules. We can read the equations in liters as long as it's a gas. That makes sense? So that's why that silly, it may have seemed strange to start off by interpreting the equation, but it makes it so we can make all of our conversion factors. That's why we do it. Okay? To think about it in terms of little pieces. So that means on our diagram, we have another shortcut. Last one we did molecules to moles to moles to molecules. But now I just said, hey, we can go straight from here to here. Oops, not all the way to there, but from here to here, using the numbers out of the equation. It doesn't work grams to grams, though, because different numbers of pieces weigh, the same number of pieces weigh different grams. So it won't work grams to grams. Grams to grams is the one it won't work for. The other two it will. Make sense? Okay. So that makes this problem a lot shorter. Yeah, you can do it in your head, but you got to prove it's right. But you can actually do this one in your head.
CO2 has no mole, has
One.
and
CH4 has one.
So it's basically just 4.7 times 10 to the 24 times 1.
Yeah, divided by 1.
Yay.
4.7 times 10 to the 24th molecules of CH4. Got it right this time. Change molecules to CH4. Normally go to moles, but I can go to molecules because I can read this equation as 1 molecule of CH4 will make 1 molecule of CO2. And that makes the math really easy. Yeah. Do my units cancel out? Yeah. Is the thing inside the parentheses true? Yeah, 1 molecule is 1 molecule makes 1 molecule. So that's what you have to make sure. Okay. So but you can't go grams to liters that way. You got to stop at the mole and change chemicals at moles. So if you've got different units, you got to get to moles. If you've got grams, you got to get to moles. If you're going liters to liters, you can skip the mole step. Going pieces to pieces, you can skip the mole step. Make sense? So we really didn't learn anything new. We just found a shortcut to do things we were already doing. Right? So that's all I got today. So, numero tres. I got lazy this time. I'm going to make you use your own paper. Oh no. You can use the back of this one if you want to, but you're going to spend your time flipping. But should be happy news down in the bottom corner. Okay. Okay. And I don't want you to be tricked. Okay. So I need you to read number 3 on there.